Okay, so on my last video, we talked about introduction on fault analysis. I basically discussed this example and then how to get the pre-fault conditions. It's basically just your load flow. If the circuit is very small, you can just use circuit analysis. Madali lang siya. And then I introduced you to symmetrical faults. Basically, I introduced you to what are faults, and then I demonstrated a symmetrical fault here. Okay, so and what is the fault point? Yeah, it's basically the point where your fault occurs. Now, I'll continue this example. So at the very instant of your fault, at the very instant that your fault happens, basically this is how your currents would look like. You basically have the fault current here. It's basically the current that is flowing at the shorted path. And then this fault current is basically from two elements. Yeah, you have the fault current contributed from the generator, as contributed by the generator, and you have the fault current as contributed by the motor. This is the reason why we want to include that back EMF. So the idea here is when your short circuit happens, basically, when you have a motor, you have discussed this before on your machines courses. So your motor is basically a machine that converts electrical power to mechanical power. So when you have a short circuit here, your let's see this one. Okay, this one. Okay, so your motor is basically a machine that converts electrical power to mechanical power. So it should receive an electrical power somewhere, and that electrical power is coming from here, your generator, delivered through this line. When your short circuit occurs, when your short circuit happens, your motor, well, it's still a machine that converts electrical power and converts it to mechanical power. It's still connected to the generator. However, your generator is no longer supplying this motor because it sees this shorted path here. So your generator is no longer supporting this motor. So in a sense, your machine, this machine, is no longer a motor. So why it's no longer receiving electrical power? Okay, well, it's still a motor, but it's no longer receiving electrical power. So why is it still here in the diagram at the very instant that the fault happens? So why do you still have this? Well, it has something to do with transient. The idea is because when you have a motor and it received no power, at that very instant it will not stop turning because of inertia. So at that very instant, it is turning with no electrical power. Therefore, it will act as a generator. Therefore, if it is acting as a generator at the very instant that the fault happens, this short circuit here is being supplied by actually two generators. At least for this example, your actual generator and your motor turned generator. Of course, this motor will eventually stop contributing power, this IFM, because eventually if it's receiving no power, eventually the rotor will stop rotating. So eventually it will stop rotating, it will stop contributing to the fault. But at the very instant that the fault happens, it will act as a generator. So you have a fault current here that is a contribution of the generator here and this motor here. In pre-fault, in normal operation, the flow of current is actually going this way. But in faulted conditions, this is the flow of current from the generator and this is the flow of current from the motor now. And the sum of those two is this fault current. So that's basically these equations here. So you can get the fault current from the motor and the fault current from the generator by just using Ohm's law. Well, this is a very small network, so it's really easy to solve for the currents. For more complex networks, you'll probably need to use load flow. Okay, so to solve for the fault current in the motor and the generator, then you just use Ohm's law. I is equal to V over Z. So it's just EM divided by 0.1. It's basically this loop here. You perform this loop here, and then and then for the current from the generator, it's basically this loop here. So that's the current from the generator. It's from this loop here. So it's EG over J.3 and EM over J.1. So how about EM and EG? So how do we get this EM and EG? This is basically your EMF from the generator, internal EMF, and this is your internal EMF, back EMF from the motor. So you get this from the pre-fault conditions. Why? Because at the very instant of the fault, you don't expect EG and EM to suddenly change. It's just like your sequential switching on transients. Okay, you assume that at the very instant that you switch from one condition to another, the pre-switching parameters are still the same. So here the voltages are still the same. You still have the same EG, you still have the same EF at the very instant that the fault happens. So how do you get this? Well, you get this EG and EM from this pre-fault condition, because this is your condition before the fault. This is basically your EG, this is your EM. So you just perform your circuit analysis on those two. Basically your V2 here, you know that V2 is 1 angle 0, and by KVL, you just perform this KVL here, V2 minus this voltage drop, that gives you EM. And then on pre-fault condition, we already solved for V1, so we already know this voltage here. So this voltage plus this voltage drop is just this EG. So how do you get the voltage drop? The current flowing here is just IM. So you can easily get the voltage drop of each impedances. Okay, so you just use those two equations, then you get EM and EG. Of course, EG is greater than V1 because the power flow is from EG to voltage to bus 1, and EM is less than bus 2 voltage because the power flow is from bus 2 to EM. Okay, so using EM and EG from these two values, we can get the values for IFM, IFG, and IF. So as you can see, pre-fault, let's look at the pre-fault. This is your line current, this is your motor current at pre-fault, before fault. This is 0.5 per unit. Now at the instant of fault, you have the motor experiencing 9 per unit. So imagine the sudden increase in the current when that fault happens. So that's basically why you have to design your protection systems. You have to consider the transients because of this. It increases by it's more than 10. Yeah, well, anyways, I guess I scaled the problem badly, but yeah. And then your generator is now experiencing 3.7 as compared to 0.5. Now if you get the fault current, it is just IFM plus IFG. So this is your fault current. It's 13.33, angle negative 90 per unit. This is your fault current on single line diagram. That's the single line diagram. So how do we interpret this on your three-phase line? So on your three-phase line, These are your fault currents, IA, IB, and IC. Basically, since your single line diagram is just a representation of one phase, and it's just like your per phase analysis, your system is still balanced, you just displace the currents by 120 degrees, then you get IB and IC. So you have IFA as 13.33 angle negative 90, B as angle 150, C as angle 30, and then all of them goes to ground, and they basically add up to 0, and that's your fault currents. So this is basically your fault analysis. You have a 3-phase fault here occurring at bus 2. Okay,